Discussion video assignment, Local Resting and Action Potentials by Sarah Wilwert. Resting membrane potential is a stable voltage across the membrane of an unstimulated nerve. When a neuron is at rest and is capable of and ready to send a signal down its length, the ICF has a measured value of negative 70 millivolts. This value is referred to as the resting membrane potential. The negative value means there are more negatively charged particles unequally distributed between the extracellular fluid, which is out here, and the intercellular fluid. A neuron uses sodium and potassium pumps to continually make sure that sodium ions exist in a higher concentration in the ECF and that potassium ions exist in a higher concentration in the ICF. As you can see in the resting membrane, the plasma membrane, the gates are closed, not allowing anything to flow between. Stimulation of a neuron causes local disturbance in the membrane potential. Generally, the response begins at the dendrite and spreads across the soma and travels down the axon and ends at the synaptic knobs. Neurons can be stimulated by chemical, light, heat, and mechanical force. When the dendrite is stimulated, its sodium gates will open and the sodium will go into the ICF, as it shows here. This disrupts the negative 70 millivolts resting membrane, causing it to become more positive. Any shift in the membrane potential in a positive direction is called depolarization. The opening of the sodium gates and the diffusion of the sodium ions into the ICF at the site of the stimulation causes neighboring sodium gates to open as well. If strong enough, this current can progress through the plasma membrane of the soma and possibly to the axon hillock region. This kind of signal is called the local potential. They are graded, meaning they vary in magnitude depending on the strength of the stimulus. The more stimulation that occurs, the more sodium channels that will open and the more sodium ions will enter the ICF, depolarizing the membrane to a greater and greater degree. So these sodium channels and potassium channels are across the whole plasma membrane. They are decremental, meaning that the current gets weaker the farther they go away from the site of the stimulation it gets. They are reversible, meaning that if the stimulation stops, the membrane will return to its resting potential. This is due to the fact that the sodium gates will close again without stimulation and the pumps can return the sodium ions to the ECF. An action potential is more dramatic change produced by voltage-gated ion channels in the plasma membrane. The axon hillock and the axon beyond have 7 to 10 times the number of sodium and potassium gates as the dendrites and soma do. And if a local potential is still strong enough when it reaches the hillock, it can trigger a much more change in the polarity and membrane potential. This is called an action potential. If a neuron is said to be sending electrical signals down the axon towards target cells, then it is actually these action potentials that are being transmitted down the axon. Action potentials differ from local potentials in the following ways. They follow an all or none law. If a local potential that reaches the hillock is strong enough to trigger an action potential, the action potential will occur at full strength. If not, no action potential occurs. So action potentials are not graded. They are non-decremental. Action potentials maintain their full strength down the entire length of the axon regardless of the distance. They are irreversible. Once an action potential starts, it cannot be stopped. And as you can see, the channels are open. And that concludes my video.